Signals are everywhere. From the music you stream, whether you are discussing radio or cell phones, even the Wi-Fi you use. But how do we break them down and manipulate them? That's where Fourier theory and filters come into play, as well as their vital functions in electronic communications. Let's dive in. Now let's talk about the Fourier theory. The Fourier theory was discovered in 1826 by Jean-Baptiste Fourier, a French physicist and mathematician. It is an infinite mathematical series that Fourier used in his analysis and design of heat and thermodynamic systems. It was later discovered that it could be used in almost any engineering analysis, including mechanical and electrical or electronic systems. The Fourier theory shows the relationship between the time and frequency domains. It provides a way to represent complex, non-sinusoidal signals as the sum of harmonically related sine and or cosine waves. This theory states that any complex repetitive non-sinusoidal waveform may be expressed mathematically as a fundamental sine wave at the signal frequency plus an infinite number of harmonic signals of varying amplitudes and phases.
This is a figure that shows a sine wave and its harmonics. A harmonic that is a sine wave whose frequency f is some integer whole number multiple of a fundamental sine wave frequency. For instance, determining the fundamental from a harmonic is straightforward, such as if the second harmonic is 2400 Hz, what is the fundamental? Here, we have an equation that acquires the fundamental sine wave 1200 Hz from a second harmonic 2400 Hz sine wave by simply 2400 Hz divided by 2 or 1200 Hz.
Fourier square wave, the non-sinusoidal waveform most used to illustrate the Fourier theory, is the square wave. A square wave is a rectangular pulse train that has a 50% duty cycle. If put through a rigorous Fourier analysis, the square wave is shown to be made up of fundamental sine wave and an infinite number of odd harmonics, like third harmonics, fifth harmonics, and etc. For an AC square wave centered on zero, the Fourier expressions state that if you take a sine wave at the same frequency as the square wave and add it into the odd harmonic sine waves at the correct amplitude, the resulting frequency will be a square wave. The figure illustrates this idea. Here, only the third and the fifth harmonics are added to the fundamental, and the resulting component is already beginning to approach the square wave shape. Let's go back to the first figure, where only the fundamental sine wave and the third harmonic of the sine wave is used in order to create a square wave. Here, I have added in the figure the line between the peak of the fundamental sine wave and the composite sine wave that is resulting from the addition of the fundamental sine wave and the third harmonic. As you can see here, I have added the sine wave that is above the horizontal axis and the one that is below the horizontal axis is subtracted in order to create this approximation of the square wave. Here, we are showing another method or another view in order to visualize the Fourier theory in a much better way. Here, the rotating circles represents individual sine waves corresponding to the frequency of the fundamental and harmonic sine waves. Each circle rotates at a speed proportional to its frequency. When these motions are summed together, they produce the final composite waveform, as shown in the connected figure. This geometric representation beautifully illustrates how Fourier theory combines harmonics to create a complex signals, such as a square wave and triangle wave and sawtooth wave that would be shown further in the video. As we have shown in the previous example and this current one, as more of the odd harmonics are added in, the side of the waves becomes stiffer and the top becomes flatter. Frequency domain plot of the square wave. Fourier analysis make it possible to think of the signal or a waveform as a combination of fundamentals and harmonics of different amplitude. In the frequency domain plot of a square wave, the amplitude of the harmonics decrease in proportional to their frequency. This is shown in the equation for the square wave given earlier, and this is also shown in the example given earlier. This is done in order to create a much flatter surface at the top of the square wave. The DC component is shown dash and may or not be present. It is not present in this example.
The time and frequency domain of the square wave. In this figure, the relationship between the time and frequency domain is shown. Given the time series, we can break down signal into weighted sum of the sine waves. Here, showing the 6 components of the signal. Each one has the 3 features: frequency, amplitude, and phase. Here, we see the amplitude of each component plotted against its frequency, and show how the time and frequency domains are related. The square wave discussed earlier is used as the example. The result is 3-axis dimensional view.
Frequency domain of a pulse train. Harmonics are distributed in a repetitive pulse waveform. When the peaks of the fundamentals and harmonics sine waves are connected to form a curve, it is called the envelope. The shape of the envelope is unique mathematically and is referred to as sin x over x or sin c curved. Some of the higher harmonics lie below the frequency waves, indicating 180 degrees phase shift. The key points on these curves are the places where the sin c curve crosses the frequency axis. These points are determined by the pulse width tau. The first crossing occurs at 1 over 1, the second at 2 over tau, the third at 3 over tau, and so on. And at wide pulse width, there are larger lower harmonics. As the pulse width narrows, the lower harmonics are diminished, and a larger number of higher harmonics appear.
The triangular wave in exhibit the fundamental and anharmonics as the Fourier expression below shows. But notice how the third harmonics does not go positive initially, it goes negative instead, indicating a 180 degrees phase shift. This figure shows the frequency domain plot of the triangle wave. The inverted third harmonic is indicated in the frequency domain plot as a line below the horizontal frequency axis.
Fourier sawtooth wave, or simply the sawtooth wave. The sawtooth wave contains the fundamental plus all the odd and even harmonics. This figure shows a sawtooth wave synthesized with a sine wave. The fundamental, the second, and the third harmonics are added together to get a composite wave that begins to resemble a perfect sawtooth. Obviously, the more higher harmonics are added, the more the composite wave began to resemble a perfect sawtooth. Here, we have a graph that shows the frequency domain plot of the sawtooth wave. As you can see here, as the higher harmonics are added or the higher frequency are added, the amplitude of the frequency begins to taper in. This is in order to create a better and better sawtooth waveform. Because if you add a much higher amplitude at the higher frequency, it would change the shape of the sawtooth wave. This is the only way that you could create a sawtooth wave using the sine wave. In this example, as you can see, the fundamentals are shown at the first one, then it shows the rest of the harmonics up to 10. Here we have a video of the sawtooth waveform with its mathematical expression shown below it. As you can see here, the waves change and began to resemble a better and better sawtooth waveform as we add more harmonics into the sine wave.
Now, we will explore an important concept in electronics, the relationship between rise time and bandwidth. This is a fundamental topic in signal processing and communication systems. Let's start with some definition. Rise time. It is the time taken for a signal to rise from 10% of its maximum value to 90% of its maximum value. Bandwidth. This refers to the range of frequencies a circuit can process or transmit without significant loss. Rise time and bandwidth are inversely related. As the bandwidth of a system increases, the rise time of a square wave decreases, allowing faster signal transitions. Conversely, if the bandwidth is limited, the rise time becomes slower. Why this relationship exists? A rectangular wave, like a square wave, theoretically consists of an infinite number of harmonics. In practical circuits, we can pass all harmonics. Bandwidth limits are imposed and higher frequency harmonics are attenuated. As more harmonics are filtered, the sharp transitions of the wave are smoothened, resulting in increased rise and fall times. When only the fundamental frequency is passed, the waveform resembles a sine wave and rise and fall times are maximized. The relationship between rise time and bandwidth is given by the formula bandwidth is equals to 0.35 over rise time. For example, consider a pulse train with a rise time of 6 nanoseconds. Using the formula, bandwidth is equals to 0.35 over 6 nanoseconds is equals to 58.3 megahertz. This means the minimum bandwidth required to pass the signal is 58.3 megahertz. This relationship is widely used in communication systems to determine the required bandwidth of amplifiers and circuits for accurate signal processing. By rearranging the formula, we can also calculate the rise time if bandwidth is known. For instance, rise time is equals to 0.35 over bandwidth. If a circuit has a bandwidth of 50 megahertz, the rise time will be rise time is equals to 0.35 over 50 megahertz is equals to 7 nanoseconds. All in all, rise time and bandwidth are critical parameters in designing and analyzing communication systems. By understanding the relationship, engineers can ensure signals are transmitted accurately and efficiently.
So let's talk about filters first. So what is filters? Filters are electronic circuits that selectively allow or block specific frequencies or frequency ranges of electrical signals. They're essential components in numerous applications, from audio systems to medical devices, power supplies, and radio frequency systems. So imagine a world without filters. Audio systems would be plagued by unwanted noise and distortion. Medical devices would struggle to accurately diagnose patients due to interference. So power supplies would be inefficient and unreliable. So here are table of contents that we're going to discuss. First, the difference between the passive and active filters, followed by low pass filters, high pass filters, band pass filters, and last the band reject or the band stop filters. So what is the difference between active filters and passive filters? So active filters use active components such as op amps and transistors. So op amps means operator amplifier, while passive filters use components such as RCL or the resistor, capacitor, or inductor. Then active filters consume power. Then passive filters no power consumption. Active filters more and complex design than the passive filters quite simple design. And active filters higher cost. Then passive filters low cost. Broader frequency ranges sa active filters. Then sa passive filters, limited frequency range. And higher gain. Passive filters, limited gain. And less sensitive to component tolerance ang active filters. And passive filters, sensitive to component tolerance. So here are the advantages and disadvantages of active filters. So the advantages of active filters: first, higher gain, broader frequency range, improve accuracy, lower component count, and better signal to noise ratio. So there the disadvantages of active filters: higher power consumption, more complex design, requires power supply, and higher cost. Then in passive filters, the advantages and disadvantages. First, the advantages: simple design, low cost, no power consumption, high reliability, low noise. Then in disadvantages, limited frequency range, limited gain, sensitive to component tolerance, and higher component count. So here is the circuit diagram of active filters and passive filters. So as you can see, the active filters are more on complex design than the passive filters that are quietly simple. So for me, passive filter is much better than active filters because of its simple design.
Low pass filter. A low pass filter allows low frequency signal to pass through while attenuating high frequency signals. This makes it essential for various applications like audio processing, communication system, and electronic circuits. By filtering out high frequencies, it ensures that only the desired lower frequencies are retained, providing a smoother and cleaner output. Characteristics: Cut-off frequency. This is the point that separates the pass band or low pass frequency from the stop band high frequencies. Signal below this frequency pass through while signals above are attenuated. And pass band, this is the range of frequencies that pass with minimal attenuation. And the last, stop band. Frequencies is this range are significantly attenuated, reducing their impact on the output. And the types: first order low pass filter has a 6 decibels per octave roll off, and second order low pass filter offers a sharper roll off at 12 decibels per octave, and higher order low pass filters provide even steeper roll off for more precise filtering. These types define how quickly the filter attenuates the high frequencies beyond the cutoff point. This is the formula of low pass filter. First order low pass filter, Fc equals 1 over 2 pi Rc. A low pass filter can also be implemented with an inductor and resistor. and Fc equals R over 2 pi L. Fc is the cutoff frequency, R is resistance, C is capacitance, and L is inductance. Second order low pass filter, Fc equals 1 over 2 pi square root of LC. This configuration adds an additional reactive components, either an inductor or capacitor, increasing the stiffness of the roll-off. And low pass filter diagram, the circuit diagram shown as a basic RC filter. The resistor and capacitor work together to determine the cutoff frequency, effectively controlling which frequencies are allowed through the circuit.
High-pass filter. A high-pass filter, HPF, is an electronic filter that allows high-frequency signals to pass through while attenuating, reducing the amplitude of low-frequency signals. In other words, it filters out low-frequency noise and allows high-frequency signals to pass through. A high-pass filter is an electronic circuit that allows signals with frequency above a certain cutoff frequency to pass through while attenuating, reducing. This filtering process is achieved through the use of components like capacitor and resistor, which interact with the incoming signal based on its frequency by carefully selecting the values of these components. The cutoff frequency can be precisely tuned. High-pass filters have numerous applications, including audio system and etc. Low-frequency noise from microphone, image processing, and communication system. And there's a three types of high-pass filter: active high-pass filter, passive high-pass filter, and digital high-pass filter. Active high-pass filter is an electronic circuit that selectively allows high-frequency signal to pass through while attenuating low-frequency signals. Unlike passive high-pass filter, which only resistor and capacitor, active filters incorporate operational amplifiers to amplify the signal and provide precise control over the filter's characteristic. And the passive high-pass filter. A passive high-pass filter is an electronic circuit that selectively allows signal to frequency above a certain cutoff frequency to pass through while attenuating signal of frequency below the cutoff. It composed of passive components like resistor and capacitor. And the digital high-pass filter. A digital high-pass filter is a digital signal processing technique that selectively allows high-frequency components of a signal to pass through while attenuating low-frequency components. It's like a digital sieve that separates the high-frequency gains from the low-frequency. This is achieved by applying the mathematical algorithm to the digital signal, which effectively modifies the frequency spectrum of the signal. High-pass filters have numerous applications in various fields. In audio processing, they can be used to remove unwanted low-frequency noise or to emphasize higher frequency for a brighter sound. So the circuit shown is a two-stage high-pass filter. Each stage consists of a resistor R1 and R2 and a capacitor C1 and C2. High-pass filter allow high-frequency signals to pass through while attenuating low-frequency signal. And in stage 1, the input signal V input is applied across the capacitor C1. Capacitor behavior at high frequency, the capacitor acts like a short circuit allowing the signal to pass through to the resistor R1. The resistor R1 offers some resistance to the signal, but at high frequency, its impedance is relatively low compared to the capacitors. The output of stage 1 is the voltage across the resistor or R1. In stage 2, the output of stage 1 becomes the input to stage 2. Capacitor and resistor behavior similar to the stage 1, the capacitor C2 and resistor R2 work together
to attenuate low frequency signal while allowing high frequency signal to pass through. The final output of the filter V output is the voltage across the resistor R2. The frequency response of a high-pass filter is characterized by a cutoff frequency or FC. This is the frequency at which the filter starts at the attenuate the signal. For this two-stage filter, the overall cutoff frequency will be lower than that of a single-stage filter, providing a sleeper roll-off in the low-frequency region. The cutoff frequency determined by the values of the resistor and capacitor in each stage. The higher the cutoff frequency, the more high-frequency signal will be allowed to pass through. The steeper the roll-off of the more effectively filter attenuates low-frequency signal. High-pass filters are used in various applications including communication systems to filter out unwanted low-frequency interference to isolate specific frequency bands.
A band-pass filter is an electronic circuit or device that allows signals within a specific frequency range known as passband to pass through while attenuating or rejecting signal outside this range. The passband is defined by a lower cutoff frequency F1 and an upper cutoff frequency F2. And there are three types of bandpass filters. First, active bandpass filters use active components like OP-amps, transistor, or IC. And the second one is passive bandpass filter. Use passive components like resistor, capacitor, and inductor. And the last one, digital bandpass filter, implemented using digital signal processing techniques. And there are three advantages of bandpass filters. It it improves signal to noise ratio by rejecting unwanted frequency. And second, reduce interference, minimize electromagnetic interference and radio frequency interference. And the last one is increase selectivity, allow specific frequency to pass through while rejecting others. And there's also a disadvantage of bandpass filters. Component components complexity active required more complex circuitry. Second, insertion loss can introduce signal into attenuation. And the last one is frequency drift can be sensitive to temperature and the component's variation. So bandpass diagram. There are three components. A bandpass filter components typically consist of input, the input signal to be filtered, and the second one is filter circuit, the electronic circuit that implements the filtering function. Common implementation included RLC or resistor, inductor, and capacitor circuits. Active filters, OP filters, base, and etc. And the last one, the filtered signal. Bandpass bandpass filter is essential components in many electronic systems, allowing specific frequencies range to pass through while rejecting others. Understanding the characteristic types and design consideration of bandpass filter is crucial for effectiveness implementation in various applications.
Band stop filter. A band stop filter, also known as a notch filter or a band reject filter, is an electronic filter designed to block or reject signals within a specific frequency range while allowing frequencies outside this range to pass through.
This filter is widely used in applications where certain unwanted frequency, such as noise or interference, need to be removed from a signal. Applications: audio processing used to remove hums or interference from audio signals such as 60 Hz power and line hum. Radio frequency communication helps to block interference or certain unwanted bands within communication systems. Medical devices filter out unwanted frequencies from sensitive equipment like ECG or EEG machines. Instrumentation removes noise from sensitive measurement systems. Band stop graph. In electronic communications, a band stop filter graph is essential for visualizing how the filter affects different frequencies. The graph typically shows frequency on the x-axis and the gain or termination on the y-axis. This is commonly called as the frequency response graph for the filter. So the band stop filters is reversed from the band pass filters. Band stop filter diagram. So a band stop filter diagram typically includes a visual representation of the circuit used to implement the filter as well as its frequency response. This circuit diagram and its components as well as how they contribute to the filters and functionality